All right, guys, today's lesson's on what we call periodicity. As you might imagine, it's related to the periodic table. He says, bruises I can handle, it's icy hands I have a problem with. That's what that guy's saying. All right, little review here, guys.
So electrons fill sublevels of lower to higher energy. And within each energy sublevel, orbitals are filled with one electron until all orbitals contain a single electron. Orbitals can hold two electrons each, because the spin of each electron is opposite.
Okay, if you guys saw in the previous illustration, right, you saw those funky shapes around the nucleus. That's because the orbitals are not nice spherical orbitals necessarily, but they can take all kinds of shapes where you can most likely find the electrons that are orbiting that nucleus. And then we have like S, P, D, and F orbitals.
The atom has a small nucleus of protons and neutrons, which is responsible for most of the mass.
The electrons are in a cloud surrounding the nucleus, made up of various energy sublevels.
Within each energy sublevel, orbitals are filled with one electron until all orbitals contain a single electron. Then, a second electron can be added. The periodic table indicates the order in which electrons are added.
So guys, today we're going to really show finally the link between atomic structure, how electrons are oriented around the nucleus, and how they are actually placed in the periodic table. Here we have Mendeleev. I'm going to ask you guys on a live session where you think this guy is from, but you guys can probably guess what this guy's credited with, not discovering, but creating. That would be our modern periodic table. This guy says you don't have to write this down. The card player begins arranging his hand for maximum sense. Scientists do the same with the cards they gather. You guys think about it. If you guys play cards, I don't know if you guys are familiar with cards, whether it's Go Fish or Uno or whatever, or regular cards like poker, right? You think about regular cards, you have aces, you have diamonds, spades, clubs, and what's the other one? Diamonds, spades, clubs, and hearts, right? You think about when you get a hand, when someone deals you a hand, what do? You first try to arrange it. You might arrange it by number, you might arrange it by suits, like I just said. And why do you do it? So you can better understand the cards that you have. And it's the same thing with elements. You think we have 100 plus elements. Well, we want to arrange those in a way that makes sense, that makes it easy to get information. And so that's what we do, and that's what Mendeleev ultimately did with the periodic table. I want to show you something. Okay, we're going to look at a periodic table that exists, that would look as it would have existed in 1873. Okay, so check it out. 1872 rather. And as you guys might expect, the ones in pink, those are the ones where they knew the existence of those elements back then. So for example, back in 1872, they didn't know helium existed. They had no clue. They didn't know neon existed or gallium or germanium. They just knew the pink ones. So someone would ask, I could ask, well, how would they, think about with their limited instruments and whatever, how would have they been able to discover, how would have they known even oxygen exists, right? What makes oxygen difficult to know, right? It's a gas, and how else would you guys describe it? Isn't it colorless? So how would they come to the conclusion that oxygen exists? It could be something like this, and I don't know exactly what it was, but for example, look, here I have some magnesium. I think we've seen this reaction before. Okay, I'm going to light it. So this is magnesium metal. Magnesium is actually right here. Actually, that should be a good example. I should be wearing high safety wear. Safety first. Come on. Okay, so you guys see that? Okay, and then you guys see we have a product. I don't know if you guys can see that. It's like a white ashy product. Well, if I did this, now what I could have done before that reaction, I could have taken my magnesium and I could have weighed it. Let's say I weighed it and it was 0.5 grams. Then I would take this product and then I put it on a scale, and what's kind of interesting? Take a guess. What do you guys think would happen if I put this on a scale? What do you think I would see? You know what? The weight is actually more. Like for example, this could be like 0.7 grams. So what would be a logical conclusion? Well, we had magnesium, that strip of metal, initially that weighed 0.5 grams. Now this weighs 0.7 grams. Oh, perhaps magnesium was reacting with something in the air that we can't see, right? And then it combined with whatever was in the air, and in fact it is actually oxygen, what we actually produced there was magnesium oxide. Magnesium and oxygen atoms come together, and therefore it's not surprising that the product weighs more than the original reactant I started with because it combined with something else. So for example, that could be how they might have discovered oxygen. Okay, so anyways, so now you guys here's, with Mendeleev, so we would have put these in, so let's just look at these in order, okay? So let's just think about, Mendeleev would have studied, some of the physical and chemical properties of these elements and try to figure out, okay, how could I, place these in an organized way, right? So let's go with hydrogen first. Let's say he looked at hydrogen, and let's just use a symbol that would describe the properties of hydrogen. I'll just use a triangle, okay? And then the question would be, what might have been the next element he would have looked at? Did he know about helium then? No, he didn't. But they did know about lithium, so then he's looking at lithium. Lithium has completely different properties than hydrogen, right? It reacts in a completely different way. So we're going to give it a different symbol, let's say a circle. Then what would be the next element he might have looked at? Beryllium. He would study its properties. He realizes, you know what? Beryllium's not like any of those. I'm going to give it a different symbol, okay? Kind of think about those like suits, right? So then the next one he might have looked at was boron. Boron, completely different properties. So I'm going to give an asterisk on that. Next one he looks at is carbon. Once again, totally different properties. I'll do a smiley face on that one. Let's say nitrogen. He looks at nitrogen. Nope, completely different. What can I do now? I'm kind of running out of symbols. A check mark, okay? Then he looked at oxygen. You guys see I'm just kind of going in order. This, you could look at it. Originally, the periodic table in this case was ordered in order of atomic weight, but our modern periodic table is in order of atomic number. So anyways, there are a few deviations between those. He looked at oxygen, man, how come we'll do a heart, okay? Then he might have looked at fluorine, and then, once again, totally different properties, so we're gonna say, we're gonna give it a different, assign it a different shape. I don't know what we could do. We'll do a target, a bullseye, we'll do a bullseye. Okay, then he looks at, now get this guy, he looks at lithium, no, I'm sorry, now we're to sodium, and you now get this, guys. I know some people are probably thinking, okay, what kind of symbol could we put now? Well, he said, oh, wait a minute. He studied the properties. He saw how it reacted with certain things like oxygen and other. He's like, oh, that is remarkably similar to, what do you guys think? He found it was remarkably similar to lithium. So what am I going to do? I'm going to give it that corresponding shape, kind of representing the chemical properties of that element. Then the next one he would look at was magnesium. And he studied magnesium. Oh, wait a minute. That has similar chemical reactivity to, guess, what do you guys think? You guessed correctly. It is beryllium. So, ultimately, what do you guys think Mendeleev did? What was the brilliant thing Mendeleev did? When he constructed his periodic table, this could have been what it looked like, minus the ones that aren't that aren't colored. He took elements that had similar chemical properties, and you know what he did? He put them in the same column, right? And so that's what helps. Now, there are some exceptions, like for example, hydrogen. Sometimes hydrogen is not like any of these right here. So sometimes periodic tables will put hydrogen separate. A lot of times they'll just put it there. But so for the most part, he put elements that had similar chemical properties in like columns. All right. Okay. So that's where we get this term periodicity from. Periodicity refers to a repeating pattern of behavior. That's what we call is periodic. So here's what we mean by that. It's kind of like, oh, you know what? Normally I would refer us to a periodic table. When we say periodic, for example, let's look. You know what? Here, we'll just show this. We'll just use our old periodic table. Obviously, that's the old one from like 1872, right? But basically, he would realize this, right? So we'd say it's periodic. Basically, he would have, he'd put elements here, different properties, different properties, different properties, different properties, and then all of a sudden, oh, sodium has similar properties to lithium. Different, and then all of a sudden, oh, potassium has similar. So we call it kind of repeats. Okay, that's where we get that term periodic. It's the same reason why we would say when we have, period 1, period 2, period 3, it's a cycle. Another thing that's periodic would be like the days of the week, right? It goes Monday, Tuesday, Wednesday, up to Sunday, and then it starts what? Monday again, periodic. So one time through the pattern is a period, that would be each row. So what we're saying here is, and it's kind of takes some time to go back and forth, normally I would refer to a periodic table. When you go across, that's called a row. When it comes to the periodic table, we call it a period. So So the first row would be period 1, second row would be period 2, so forth. And this is the remarkable thing that, the brilliant thing, is pretty simplistic, but it's still pretty brilliant, is this is what Mendeleev was known for. He took elements that are chemically alike and he put them as part of the same, what we call family. He put them in the same column, okay? So we're gonna show you guys what that would look like. So I do want you guys, ideally what you guys would do, normally I would give you guys a periodic table. If we didn't have COVID, I could actually hand you a periodic table. And you guys, I would ask you guys to mark it up. So hopefully you guys have that periodic table that's in the materials section in your Google Classroom. You guys can print out and then tag it up. So what I would like you guys to do is recognize, like for example, this first group of metals, that's called the alkali. You notice the hydrogen's not there? Those are the alkali metals. Basically, we'd say they're part of the same family. They have similar, right, just like you guys, people in your family share similar characteristics. Likewise, these share similar characteristics, so we're there in the alkali metals. This right here are called the alkaline earth metals. I'm just going to do some of the more characteristic ones. The ones in the middle don't really have very similar chemical properties, so we don't indicate any particular families. These ones here, the far right, are called the noble gases. The second to last column are called the halogens. And you know what? You can call this the oxygen group. You can just call it the oxygen family. It's also called chalcogen, but we can call it the oxygen family. Okay? So those are the ones I want you guys to be familiar with. And if you just needed to write it down, you might just put this. Preferably, you guys would put it on your periodic table. If you had to write it down, once again, that first column are the alkali metals, the second column are the alkaline earth, the second to last are the halogens, and then the last ones are called the noble gases. And once again, you guys, if I'm going too fast, that's where you have an opportunity to pause the video and then take time to write things down. Okay, so now we're going to see a relationship between.
This is easy.
Here,
Chromium is element number 24. Its configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4.
Okay.
Which becomes.
I think what you guys are now seeing is there is a relationship between, you guys remember what this is called, the electron configuration. Remember, this is indicating how many electrons around the nucleus are located in which orbital. So you have to see the previous lesson, otherwise you're like, what the heck is this, right? And you can see a relationship between that and the periodic table. In fact, and what I ultimately want you guys to get to is a point where you can just use the periodic table to write the electron configuration. Remember, up until now, you guys have been using that orbital filling diagram. You guys remember with the arrows? That's what you guys would write down, okay? So it was, check it out guys, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d4, okay? Okay, let's see it, like, look at this one now.
1s2,
1s2,
2s2, 2p6, 3s2, 3p6, 4s2, 3d2.
So, if you guys, once again, you guys remember the exponents refer to the number of electrons. If you add all those up, what are you going to get? You're going to get 22. It has 22 electrons. You're right, and if it's neutral, it has 22 protons, so it should match with that. So that's what's showing you where all those 22 electrons are located around the nucleus of titanium, and ultimately how those are arranged ultimately determines the chemical properties of titanium. That's why that's important. All right, so here is something else I want you guys to do to your periodic table. Like I said, this works ideally if you have a printed periodic table, so then you can tag it up. You guys will see. Here, for example, the first two columns here, we call it the S group because the outer electrons of those elements exist in s orbitals, so that's the S group. Now you'll notice that there's two columns, which kind of corresponds with the fact that only 2 electrons can fit in the s orbitals, right? And then this group right here, we would call the p group. So the elements there have their outer electrons located in p orbitals, and what you guys will notice is there's 1, 2, 3, 4, 5 6 columns, and you guys remember, 6 electrons can fit in the p orbitals on within a specific energy level. So there's a correlation there. And then this one is the D. And you know what? At this point, I don't know if you guys can see that. My pen's going out. And then down here, you actually pull out the F. We don't talk too much about the F orbital. These are not as common elements, so we're not going to deal with those elements. So recognize S, P, and D. And so if you guys see that, then you should be able to start using the periodic table to write electron configurations. So we're going to practice that. Do you know why I pulled you over? Well, if you don't know, well, I'm not going to tell you. Hopefully you guys don't respond to cops like that. All right, so let's see how we could use a periodic table. Now, unfortunately, you know what? I might have to, yeah, you know what? So we're going to write these down because I'm going to do them separate. Sodium, potassium, chlorine, and bromine. So you guys, we're going to show you guys how to use the periodic table. So I'm going to go to another, I'm going to bring up our periodic table. Okay, 1 second, guys. Okay, so here's our periodic table. So here's how we would use that. So lithium has 3 electrons. So here's how we would do it. We would say, okay, so, these correspond, and you guys, the periods correspond to energy levels. You can just look at it like this. So this would be 1s2, and then lithium has 3 electrons, right? 3 electrons. And then the question is, where is its outer electron? On the second energy level, and it's in S1. See how this is S1, this is S2. It's in 2S1. Let's do sodium. Sodium has 11 protons, 11 electrons. So look how sodium is. So remember, all the electrons are going to be in the lower energy levels first, so they all start out the same, right? So it's going to be 1s2, and then 1s2, and then 2s2. You guys see we're going all the way down to sodium, so then it's 2s2, because remember, 2 electrons can fit in the 2s orbital as long as they have opposite spins. Then what gets filled next? You guys see we're still in the second energy level. You remember this is the p block, 2p6. You guys remember why there are 6 electrons? Because p orbitals are pear-shaped, x-axis, y-axis, z-axis, 2 on each one. That's a total of 6. 2p6. And then where's our last electron? It's located in the third energy level. You can just think about the electrons are being found further and further away from the nucleus in the s orbital, and there's 1 electron in that s orbital. There you go. Let's do potassium. Potassium, it starts out the same. Look, 1s2. Oh, I'm sorry. So potassium has 19 protons, 19 electrons. 1s2, then 2s2. Hopefully you guys are starting to get this. 2p6, remember that's the p block. 2p6, 3s2. And where the next, once the 3s is full, where the next electrons go? 3p6. And then lastly, you see the last electron's 4. It's in the s orbital, so it's 4s1. There's only 1 electron. And when I add up all those exponents, I should get 19, because that's the number of electrons. Okay. Let's go back to our slides. Okay, so this is what we did. Okay, so we showed you how you could get it from the periodic table. Now what you guys will notice is, you guys remember, these are all the alkali metals, remember? And we put them in the same family because they share similar chemical properties. The question I might have for you is, what do you guys think might account for the fact that they all have similar chemical properties? How are the what do you guys notice in the electron configuration that looks similar? Hopefully you guys noticed. So that's the question. Hopefully you guys noticed. You guys check it out. They all end S1. I was wondering if I was going to do abbreviated electron configurations. You know what? I'm going to show you guys how you can do abbreviated electrons, because I think a lot of you guys would recognize You guys see how it's kind of redundant? It's like the same thing. You can imagine when we get very large atoms, it might, it would get kind of tedious to do the same thing. So let me go back to our periodic table and show you guys. Here's an abbreviated way you can do it. Because once again, you guys, what are the electrons that we're most interested in? You guys remember from the previous video lesson? It's the valence electrons, the ones on the outer. Okay, so those are the ones we're concerned about. So here's what we can do. So for lithium, what you can always do is you can pick the noble gas that comes before the element. So for lithium, you see the noble gas that comes before is helium. So I could say its electron configuration is just like helium. What I'm saying is its first two electrons are just like helium, and then all I'm showing is the valence electrons. And yet it has, and where's its outer valence electron? 3s1. I'm sorry, 2s1. Okay, so we'll just keep going because I know you didn't get this yet. Let's do sodium. Once again, what's the rule? Choose the noble gas just before it. The noble gas before is neon. So what I'm saying is, sodium's first, we would say, for example, you guys remember this? These kind of correspond to shells. They're energy levels or shells, right? So sodium, for example, like I see lithium has 2 shells of electrons, right? It's got 2 electrons on its first shell. Its first shell is full, and then it's got 1 electron in its outer shell. So I don't really care about the electrons in the filled inner shells. I care about the valence electrons. That's why I just abbreviate like this. Let's do sodium. So once again, look, sodium has 3 shells of electrons. And so what I'll do is I'll choose neon. So what I'm saying is its first shell is full and its second shell is full. So those are filled inner shells. Those are the core electrons. I would say the first 10 electrons are just like neon. And then what am I just showing? Just the valence electrons, just the electrons that are in the outer shell. The outer electron is on the 3rd energy level, and it's in the s orbital, and I put 3s1. Look at potassium. Guys, using the same technique, I choose the noble gas before it. Remember, noble gases are right here, last column. I choose the noble gas before it's argon. So what I'm essentially saying is, I'm saying potassium's first 18 electrons are located in the same place that argon's are. But I'm not really interested in those. What am I interested in? Just the outer electrons. And so potassium, its outer electrons in the 1, 2, 3, 4. It's on the 4th energy level, s orbital, I put 4s1. And now it's going to be easier to see. What is it that looks similar about all of these alkali metals that might explain their chemical reactivities? You guys notice, somebody said they all had s1. What does that mean? They all have 1 valence electron. And that helps explain why they behave similar. Okay, let's do some other ones. Okay, and this is just kind of redoing what we just did right here. Okay, so now we've got some other ones here. So if we did fluorine, you guys, I'd hope you guys would have your periodic table at home and you could kind of follow along. But fluorine is 1s2, 2s2, 2p5. Okay. Chlorine. You guys remember, once they start to get bigger, maybe we want to do the abbreviated. So, here, I'll even show you just so we can, because I don't expect you guys to get this yet. So we're doing chlorine. Remember what we can abbreviate it. We can say its first 10 electrons are just like neon. You guys remember that's the noble gas. Remember, you don't choose the element before, you choose the noble gas before. It's just like neon. So, right, its first shell is full, its second shell is full. And then, what do I just want to show? Just the valence electrons. So where are the valence electrons located? 3s2, and then it's still the 3rd energy level, 3p5. You guys see how that works? And then the next one asks for bromine. So how would I do bromine? Choose the noble gas before is argon. I'd say bromine's first 18 electrons are just like argon's. Okay. So how many more electrons does it have? Well, 35 minus 18 it still has 17 electrons. The question is, where are those electrons? So this kind of gets there's a little extra wrinkle here, guys. You got to follow here. So bromine, I would go. It's 1, 2, 3, 4. It's 4s2. But if you guys remember from your orbital filling diagram, the d orbitals begin within the 3rd energy level. So this isn't 4, and this is the d block. Remember, there's 10 because there's 5 different d orbitals, each which hold 2. So it's actually 4s2 and then, 4s2, 3d10. That's what's going to throw you off. So the d's are always 1 less than the corresponding period. So if this is period 4, and this is the 3d, if this is period 5, this is the 40. So it's 3d10, and then what is it? It's still the 4th energy level, 4p5. Okay? So I just wanted you guys to see how we would ultimately get it from the periodic table. So you guys kind of go over it slower if you need to. But then we would do it abbreviated, right? just like I said, right? We said the first ones are like argon, and then I'm just showing the outer ones. So once again, I would ask, what might explain why all of these have similar chemical properties? Well, what you do is you see the valence electrons. Those are the ones on the outer shell or energy level. So you guys can see now. It is kind of tricky here. So you guys remember how I said you can do the outer shell? Remember you go to the last S, and then you count how many electrons after that last S, and then the last S, which it's already done. So you can see you could say these all end P5. But it's also, they actually have 7 valence electrons. I know it seems kind of weird. That's clearly 7, that's clearly 7. Someone said, hey, that's 17, Mr. Wilson. What's the deal there? But remember, these 10 electrons are within the third energy level, so those are very, very stable. Those aren't going to be gained or lost. Therefore, we don't technically count those as valence electrons, so it has 7 as well. Once again, this would explain why the halogens have similar chemical properties. Okay, and then the last ones, neon and argon. If you guys remember from the periodic table, those are the ones on the far right. Those are our noble gases. This is its electron configuration, and then argons. Remember, we can abbreviate it, and we can say argons is like neon. Neon was the noble gas before it. And then what would explain why the noble gases behave the way they do? Once again, what are the valence electrons? You go to the last S, you count out that 2 and 6 is 8. 2 and 6 is 8, they all both have 8 valence electrons. So, got a question. What can you say about noble gases back in 1872? Okay, so let's show you what that is. So we're almost done here, guys. Stick with me. Guys, so what can you guys tell me about noble gases back in 1872? Hopefully you guys would conclude, oh, those weren't even discovered. So the next question is, why do you guys think those weren't discovered? Okay, that's the question. Let me see. I could see someone say, oh, those weren't discovered because maybe those are colorless gases, colorless gases, and they just didn't know they exist. But then you guys know what I'd bring up. I'd bring like oxygen up, right? That's a colorless gas. And remember how we could see how that was formed. Remember, it combined with magnesium, it weighed more, so that's how we knew it was there, even if we can't see it. So what might explain for the fact that those were not even known? Well, if you guys were following, what you'll find is the noble gases, those all have filled outer shell of electrons. If you guys remember from the last video lesson, you remember what we said. Atoms have a tendency to gain or lose electrons in order to fill their outer shell because there's a real stability associated with it. So if you guys look at it, how many shells of electrons does helium have? It has 1 shell. What can you tell me about that shell? It's full. How many shells does neon have? It has 2 shells. It has 1 filled shell and 2 filled shells. Its outer shell is full. Same with argon. It's 3 shells. Its first, second, and even its outer shell is full. So if they're full, they're not going to have a tendency to gain or lose electrons. They're not going to have a tendency to interact with other atoms, right, in order to acquire electrons or give electrons, because they're already sitting happy, fat, content, stable. Therefore, they're going to be very non-reactive. And so the reason why Mendeleev in that day, they didn't know they existed because they didn't react with anything, so therefore it was very difficult to determine their existence. All right, guys, we will see you next time.